These are the class highlights for the Chapter 10 material for Unit 7. And in this chapter, we're only going to cover sections 1, 2, and 3. So what we're going to be talking about in this chapter is figuring out whether a correlation or a relationship exists between two variables and whether that relationship or correlation is linear. In other words, if it's something like a straight line relationship. If there is a straight line relationship, then we can find an equation for the straight line that best fits the data, and we can use that equation to do some predictions for the value of one variable given the value of the other variable. So first we'll talk about correlation. What we can do if we have a set of data with two variables is we can find what we call the linear correlation coefficient. This is a number that measures the strength of the relationship between the two variables, whether that relationship is very close to being linear or not. And we'll also talk a little bit about hypothesis testing for correlation. So the definition of a correlation is that a correlation exists between the two variables when the values of one are somehow associated with the values of the other. That just means that there may be a relationship between the two variables. So our correlation coefficient, R, measures the strength of that linear relationship. Here are some properties of our linear correlation coefficient R. First of all, the value of R is always going to be between -1 and +1. It can't be less than -1 and it can't be greater than +1. And the value of R doesn't change if the values of either of the variables are converted to a different scale. It also doesn't change if we interchange the values of X and Y. So if we define which variable is X and which variable is Y, and then we decide to switch that around, we're still going to get the same value for R. And again, R measures the strength of the linear relationship. The other thing about our correlation coefficient is that it's very sensitive to outliers. Outliers in the data points can have a significant effect on the value of R. One way that we can look at the relationship between two variables is by constructing a scatter plot. So we're going to look at a few different scatter plots and see what type of R values they would have. Here are two scatter plots where the linear relationship is somewhat strong. The one on the left has a positive correlation because if you look at the data in general, it's going up as you go from left to right on the graph. So that gives us a positive correlation, meaning that the value of R that we get is a positive number. And the closer that the R value, in this case, gets to 1, the stronger our linear relationship is. So since it's only 0.851, it's not all that close to 1. And you can see by looking at those data points that they're sort of in a linear pattern, but they're not really close together. The graph on the right, on the other hand, goes down as it goes from left to right. So this one has a negative correlation, meaning that our R value is going to come out to be a negative number. And remember that R can be anything from -1 to +1. So in this case, if we have a negative correlation, the closer our R value is to -1, the stronger the linear relationship. And you can see here that our R value is -0.965, which means it's closer to -1 than for the graph on the left that value was close to 1. And you can compare these two pictures. You can see that the one on the right has a little bit more of a straight line pattern than the one on the left. So it has a stronger linear relationship than the one on the left does. And here's another picture. In this one, the data is all spread out. There's really no linear pattern in there at all. And if you notice, our R value is 0. In general, the closer that the R value is to 0, the less linear relationship there is. And if it's actually equal to 0, that means that there's no linear relationship at all, no correlation. In this picture, the data has a relationship, but it's not a linear one. In other words, it's not in a straight line. It looks more like a parabola. So we could still find the R value for this, but notice that it comes out to be -0.087, which is very close to 0, which means that there's not a strong linear relationship here at all. Okay, what we will do with a set of data is find out what our correlation coefficient is. Then we'll look at how we determine whether we think there's a linear relationship or not. How strong does it have to be in order for us to say that there is a linear relationship? So the requirements for this are that we start out with a sample of paired data. It has to be a simple random sample. It has to be quantitative data. And the first thing we'll want to do is look at the scatter plot to see if there's any kind of straight line pattern at all. The other thing we'll look for on the scatter plot is to see if there are any outliers. If we see outliers, then we would want to go investigate and find out whether they were due to errors or not. If they are because of errors, then we would want to remove the outliers. If they're not because of errors, then we would have to consider whether to remove them or not, or whether to include them in the data or not. Okay, here is the formula for actually calculating the linear correlation coefficient. And don't write this formula down because, again, I'm not going to make you use this one. We will be finding the correlation coefficient using technology, either StatCrunch or your calculator. So this is just to show you how nasty this formula is. Now the important thing is interpreting the correlation coefficient. And here's how we do this. If we have our correlation coefficient R, then remember that R can be either negative or positive. So we're going to look at the absolute value of it, which if it's a negative number just makes it positive. We're going to compare that to a critical value that we get from this table. This table is in the back of your book and it's available on Course Compass. And this gives us critical values for a significance level of 0.05. What happens is that if the absolute value of our R is greater than the value we would get from the table, then we can conclude that there's a linear correlation. On the other hand, if it's less than the value we get from the table, then there's not enough evidence to support the conclusion of linear correlation. So here's an example. If we have data from a set of 10 observations, that means that n equals 10, and we find our R value, and it turns out to be negative 0.836, then we would look up the critical value in this table, and if we have alpha equal to 0.05 and n equals 10, then the value we would get from the table would be 0.632. Now, since our R value was negative, we're going to take the absolute value, which makes it a positive 0.836, and we'll compare that to the value we got from the table. Since 0.836 is greater than 0.632, then we can conclude that there is a linear correlation. Here's another example. In this one we have 35 observations, so our n is 35. We got an R value of 0.316. If we look up the critical value in our table, for n equals 35 we have 0.335. Since 0.316 is less than 0.335, that means there's not enough evidence to conclude that there's a linear correlation. Now we can also use software like StatCrunch to compute a p-value. Instead of looking up the critical value in the table, if we have the p-value and if it's less than or equal to our significance level, then we can say that there's a linear correlation. Otherwise, there's not enough evidence to support that conclusion. And here's an example of that. Say we have a 0.05 significance level. We found an R value of 0.117 using some data from the data sets in the book. Now, if we used software to compute a p-value for us, the p-value comes out to be 0.364. Now, what we want to know from this is there sufficient evidence to support the claim of a linear correlation? Well, since the p-value is 0.364, this works just like the hypothesis testing that we've been doing. Our p-value here is greater than our significance level. So again, we're comparing our p-value to our significance level alpha. Our p-value is 0.364. Our alpha is 0.05. So our p-value is definitely greater than our alpha. And this means in terms of hypothesis testing, our conclusion would be that we'd fail to reject our null hypothesis. This is a little bit of a review for hypothesis testing. And in this case, that means that there's not enough evidence to support the conclusion of a linear correlation. Now, you do have to be careful with data here because we're only talking about linear correlations in this class. There are other types of correlations, so there may be other relationships between the data that we could find, but we're not going to cover that in this class. And if you're going to be using that table, find your critical values, then what you want to do as far as rounding your correlation coefficient is to round it to 3 decimal places. Since the values in the table go to 3 decimal places, then you'd want to round it to the same number of places so that you can compare the two. Here's an example of some data that we're going to look at. This compares the cost of a slice of pizza, subway fare, and the CPI in certain years. So what we're going to look at is whether there's a relationship between the cost of pizza and subway fare, and whether that relationship might be linear. The first thing we want to do is look at the scatter plot of the data. And to do this in StatCrunch, what you would do is put the cost for the slice of pizza in one column and the subway fare in another column. Make sure that they match up. For this example, we're going to use the cost of the slice of pizza as our X value and the subway fare as our Y value. So if we construct a scatter plot in StatCrunch, this is what our scatter plot looks like. And notice that it does look like we could draw a straight line that would come close to a lot of these data points. So just looking at this graph, we could probably say that it's likely that there's a linear correlation here. We don't see any outliers, and our other requirements were that we had a simple random sample. We're going to assume that. And then we can also use StatCrunch to get our linear regression results. The one that we're interested in right now is our correlation coefficient, which is right here. So this is calculating our correlation coefficient is 0.9878. We're going to round that to 0.988. The other value that we're going to look at is the p-value, and in StatCrunch they actually give you two different ones. The one that you want to look at is in the row that says slope. So the p-value that we're interested in here is this one, the 0.0002. Now the other value that we can look at is r squared, which it also gives you in StatCrunch. And this is the proportion of the variation in the y values that's explained by the linear relationship between the x and the y. So if we do find that there's a linear relationship, then we can say how much of the variation in the y values has to do with that linear relationship and how much doesn't. So going back to the information that we just found, if we already know the r, we can use that to find the r squared. But notice in StatCrunch that it also gives you the r squared value right after the r value. So we could look at this and already tell that our r squared value is 0.976. But if we didn't have that information for some reason, to get that we would take our r value and just square it. So we take our 0.988 and square it, and that would give us 0.976. So that's our r squared. And what that tells us is that 0.976, or which is approximately 98% of the variation in the cost of the subway fares, can be explained by the linear relationship between the cost of the pizza and the subway fares. The other thing that tells us is that about 2% of the variation can't be explained by the variation in the cost of the pizza. Now, some common errors when we're talking about correlation. The biggest error is when people conclude that because there's a correlation, that means that one of the variables caused the other one. That's what they mean here when they say causality, is that one variable actually causes the other. Another error is in using averages in your original data. Averages or means actually suppress individual variations, so it may give you an inflated correlation coefficient. And the third one we've already talked about. There can be some relationship between the x and the y, even if there's not a linear correlation. There can be some other type of relationship. Okay, now let's talk about regression. And this, we're still talking about the same thing. We're just going to find the straight line that best fits the data if there is a linear relationship. And this straight line we call a regression line, and the equation for that line is called the regression equation. What this does is it gives us a relationship between x and y that we can actually see on the graph. And if you remember the last algebra class you had, I'm sure you talked about straight line equations, and the slope-intercept form is y equals mx plus b. What we're going to do, or what our software is going to do for us, is it will find that slope and that y-intercept that go into that equation. So here's what our regression equation is going to look like. This is just another form of that slope-intercept form of a line. So this is our intercept, our y-intercept. Is the b0, and the b1 is our slope. And the line that we find for this, or that our software finds for us, is the one that comes the closest to the most data points. And again, we're going to round to 3 significant digits with our y-intercept and our slope. So let's go back to our pizza and Subway fare example. We're going to use the same data and the same information from StatCrunch to find the equation of the regression line for this. So, and in StatCrunch, it will give you all this information at once. You don't have to do it piece by piece. So in this display from StatCrunch, this is what's giving us our regression line. And notice that it actually gives you the names of the variables. Whatever you named your columns, I named them pizza and Subway when I put this data in. So this would be the same as X, and this one would be the same as Y. It even tells you up here that your independent variable is pizza. An independent variable is going to be the same as X. Your dependent variable, which is Y, is Subway. So we could write down our regression equation with the Y and the X instead of the pizza and the Subway. So here would be our regression equation down here. And what we can do with this is we can use this to predict other values of Y that we don't already have. Now let's look at our scatter plot again with our regression line drawn in there so that we can see how well it fits. Notice that we're coming fairly close to most of these data points. There are a couple that aren't quite as close to the line, those two, and this one's not quite there, but for the most part this line is fitting our data pretty well. And that matches with the information we had before about the correlation coefficient and the p-value. Now the next question is, when can we use our regression equation to make predictions and when can't we? So here are 3 things we want to look at to see whether we should use our regression equation for predictions or not. Number 1, we should look at the scatter plot, compare our scatter plot and our regression line, and see if our regression line fits the points pretty well. We also should look at our linear correlation coefficient R and either compare it to critical values in the table or look at our p-value to see whether we can conclude that there's a linear correlation between the 2 variables. The third thing is that we really only want to use our regression line for predictions if our data doesn't go too far beyond the scope of our available sample data. Predicting too far beyond the scope of the sample data we already have is called extrapolation, and it can be used in some cases, but if we extrapolate too far out from the sample data that we have, we can get very bad predictions. Now, if we go through those first 3 items and we don't have all of those things, then our regression equation probably isn't going to be very useful for making predictions. If that's the case, then the best predicted value of a variable is the point estimate, which we've already been talking about in the last couple of chapters. The point estimate is going to be the sample mean of the data for that variable. In other words, if our regression equation isn't going to be a good model for our data, then the best predicted value for Y is going to be Y bar, which is just the sample mean for the Y values. Here's another example with our pizza and Subway fares. If we wanted to predict a value of Y, for example, if we knew that the cost of a slice of pizza in 1998 was $1.50, and this wasn't one of our data points that we already had, if we had this information, we could use that to predict our Subway fare for that year. So we would go back to our regression equation, since we did find that there was a linear relationship between the 2 variables. Here was our regression equation, and what we would do, put the 150 in here in place of the X, and then we would calculate this out, and that would give us our predicted value for Y. So we would take we would put the 150 in there in place of the X. We would go ahead and multiply these 2 and then add and that would give us our predicted subway fare. Okay, here's a problem for you to try. If we have 4 pairs of data, we get an R value of 0.942, and we find a regression equation from StatCrunch or other sources of y hat equals 3x. We also know that y bar, which is our sample mean for the y values, is 12.75. What we want to know is what's the best predicted value of y if x equals 2.5. So the first question here is, can we conclude that there's a linear relationship or a linear correlation? That's the question that we have to ask first of all. Now, since we had 4 pairs of data, that means that n is equal to 4. And that would give us 0.950 for our critical value. So again, we're going to compare our critical value and our correlation coefficient. So if we take our correlation coefficient and our critical value, the correlation coefficient is actually less than the critical value. That tells us that there's not enough evidence to conclude that there's a linear correlation. If there's not a linear correlation, then we don't want to use our regression equation to make predictions. So in that case, we're just going to use our sample mean for the y's as our best predicted value for y. So we would say our best predicted value is just the 12.75. Now, if we had found that there was a linear correlation, then we would plug our x value into our regression equation and use that to make our prediction. So here's the correct answer for this question was 12.75.